Okay, so we just finished lesson one and we were introduced to waves and the main categories of types of waves. Now we're going to go into another type of wave. Today we're going to be talking all about sound waves and their properties, which is another way of saying their characteristics. So, what actually produces sound? In lesson one, you took notes and you saw that a disturbance or a vibration causes a wave. And it's the same idea for sound. Every sound is caused by something that vibrates. All right. So that's what you need to write down. You don't need to write down this example, but I have it here because it can be helpful for understanding. So it says, for example, your friend's voice are produced by vibrations in their vocal cords. So those vibrations from your vocal cords is what causes the matter in the air to move, right? And it also gives an example of a loudspeaker. So it forces vibrations from the speaker, the carousel in the speaker, which causes the matter to start to vibrate. So, same idea as any other wave, you need some form of disturbance or vibration to start the wave. So, we talked about mechanical waves yesterday and how these are a type of wave that need matter to travel through, right? And remember, matter is anything that takes up space and has mass. So basically, you can measure it and it has a volume. All right. So that is because sound waves need some sort of particle to actually transfer that energy. Right. So the way that sound waves travel is they create a vibration, and that vibration forces a particle to move. So if you're talking about me shouting across the room, right, the medium is air. That's the matter. So when my vocal cords vibrate, they send energy through the air particles. And as those air particles bump into each other, each particle that bumps into each other is continuing that energy, continuing that wave until it reaches your ear. If I didn't have any particles, I didn't have any matter to travel through, then there would be no way to transfer that energy from my vocal cords to your ear. So that matter that sound waves travel through is called a medium. Know that, star that somewhere in your notes. And they can travel through any type of matter, right? And they cannot travel through a vacuum. So yesterday we talked about some waves that can travel through a vacuum, like electromagnetic waves that can travel through space. Sound waves can't really do that. So yes, sound waves can travel through different mediums, but how fast they travel through different mediums varies. And I know I mentioned in our last lecture that sound travels faster through a solid, and sometimes that doesn't seem like it would make sense, right? You would assume it would travel faster through air, but it's actually because, like I said, sound needs those particles to bump into each other in order to transfer that sound. And so in a solid, the particles are really close together. And so since they're close together, they can transfer that energy easier than like in a gas where the particles are all over the place. All right. Now, the speed of the wave does not depend on the loudness. We'll talk about loudness here in a second, but loudness is not equal to the speed of the wave. So if you have that misconception, don't think about it that way. This table over here with the different sounds through different mediums, you don't need to write that down. You don't need to know that, but I have that there as like a comparison for you so you can kind of see how drastically it actually changes from one medium to another. So some other things that can affect how fast sound travels. So we know the medium, it travels faster through a solid, but also the temperature. Because if you increase the temperature of particles, it gives them more energy. So they're allowed to move faster, right? So even though solids already have particles that are really close together, I heat those particles up. Now those particles have a lot of energy to start bumping into each other and colliding with each other, which is what we want them to do to transfer that energy. So higher temperature equals faster speeds. So now we'll talk about loudness and intensity. So quieter sounds do not carry as much energy as louder sounds. So I just told you that the loudness is not related to the speed. The loudness is related to the amplitude, though. And remember, amplitude for a longitudinal wave is how close those compressions are, right? So really tight compressions means a high amplitude. Um, if we were talking about a transverse wave, it would be how high or low the crests and troughs are. So remembering loudness has to do with the amplitude. Basically, the more power in that wave, right, the louder it is, the stronger and tighter those compressions are going to be. But that has nothing to do with the sound. Now, intensity is the actual energy transferred, right? So the more intensity you have, the more energy, right? So that influences how far that sound can be heard. So if I were to use more energy to shout across the room, people further away from me could hear me more. Now, sometimes we confuse intensity and loudness, but remember, intensity is the actual amount of energy. Loudness has more to do with what you're hearing, and we'll talk about that in a second. So, intensity is the measure of the energy of the wave, and that's what allows you to hear further. Loudness is a little bit different. Loudness has to do with what you perceive, and what that means is what is considered loud to you is different than what is considered loud to me, which is why in some classes you're allowed to be louder than in others. So there's a general idea that the higher your intensity, the louder you are. But loudness is all about what you perceive. It's how your brain interprets the intensity of this to be too loud or comfortable. And sometimes how we grew up influences that as well. Okay, I apologize. The picture kind of got shifted over the words here. Sometimes it does that in this program, but I'll read it to you. So there's a scale for loudness. Now, the units that we use are decibels, and you may have heard this before, but when we are measuring the intensity of a sound, we measure it in decibels. So on the scale, the faintest sound that most people can hear is 0 decibels. And once you start getting above that like 100 decibel line, that's when we can start causing pain to our ears. So you can notice there, a high school cafeteria is considered to be somewhere around 80 decibels, which if 100 starts to cause pain, that means it's on the louder end. So yeah, that's just a way to kind of show you how intensity is the actual number in decibels, but sometimes that relates to loudness, but it all has to do with what you think, right? So some people can figure that a high school cafeteria is really loud. Other people might be like, it's fine. So now pitch. Pitch is how high or how low a sound appears to be. So remember, loudness has to do with the amplitude, right? And the intensity. Pitch has to do with how high it is. Pitch is related to the frequency. And remember, frequency is how many waves come by in a second, right? So basically, the faster waves, the higher the pitch. So putting those two together, frequency is a measure of how many wavelengths pass the point each second. You already have that in your notes from last time. So for a longitudinal wave, which is what sound waves are, the frequency is the number of compressions or rare fractions that pass by each second. Frequency is measured in hertz. You already know that too. So when a sound wave with high frequency hits your ears, mini compression hits your eardrums at 1 second. So that's what you need to write down. So the difference between a loud sound is that if a loud sound were to hit your ears, it would have a high amplitude. So that would be a sound wave with like a really tight compression. Whereas if a high pitched sound hits your eardrum, that is a sound with many compressions. See the difference? It's like the size of one versus how many. That's the difference between loudness and pitch. So again, I apologize for the picture being over the words. I'm gonna have to figure that one out. But again, I'll tell you what it says. So we just saw a chart that showed us the numbers of loudness, right? And we got above about 100 decibels, and that's where we started to cause pain. This one shows us numbers of different notes. You don't need to write this down, but again, this is just to show you an illustration of something you might be familiar with. And frequency we know is measured in hertz. So a healthy human ear, right, can hear frequencies from about 20 hertz to 20,000 hertz, right? That line that's kind of cut off says that the human ear is most sensitive to frequencies in the range of 440 hertz to about 7,000 hertz. And what that means are those are the ones that we hear probably in our regular day lives, the ones that we can definitely hear and interpret what they are, as opposed to trying really hard to hear what it is at like one of those other ends of 20 or 20,000. And then the last thing here, I really want you to understand this. I'm going to put a video here that I need you to watch and take notes on it because the Doppler effect is really important to understand. So basically, I want you to think, have you ever been near like a fire truck, right? And it seems like as it gets closer to you, it all of a sudden gets so much louder. But obviously, the siren's not getting louder. They don't have a volume control that they're turning up as it passes you. The reason that we hear that and it seems like it's getting louder is by what we call the Doppler effect. Basically, it means that when a source is moving, so whatever's causing the sound is moving, it causes the sound to change to the listener. And this is why. So I'm going to try to explain this, but I want you to watch the video so you can see it a little bit better. We know that waves are coming off of whatever's causing that sound, right? But as that sound is moving forward, it's actually moving through the waves it's creating, forcing those waves to actually get closer. And as those waves are getting closer together, they're creating a higher pitch because now they're coming faster, um, and they're getting a higher amplitude, so they're seeming louder. All right. So that's a general idea of what the Doppler effect is. But again, you watch that video, it'll probably make it a lot easier for you to understand. All right. And that is the end of lesson 11.2.